I tried to squeeze it all in one video and it just wouldn't fit. Welcome to OSPF Concepts Part 2. What we're going to do is wrap up the concepts of OSPF enough that we will be able to now move in an educated fashion into the configuration of OSPF. It's one thing to walk into the config of OSPF and just type in a few network commands and make it work, but it's another one to be able to type in the network commands, then verify the operation and do troubleshooting if necessary if anything goes wrong. That's what these concepts are all about. We'll start off by taking a look at OSPF's cost, which is how it finds the best way around the network. We'll then look at the key concept of the DR and the BDR, which is going to come back again and again as we look at all the different OSPF network types that it supports. Finally, we'll wrap up by looking at all of the OSPF packet types rather than just the hello, the DBD we talked about in OSPF Concepts Part 1. We'll talk about them all. I'd like to pick up right where we left off in the OSPF Concepts Part 1, which was the OSPF routers had formed neighbor relationships. They were speaking, they had exchanged all of their topology databases, and now they had to figure out what's the best one for me. Which one of these routes do I put in my routing table? So what you see on the screen right here is kind of a view that we can understand of what the router sees in its topology database. As all the routers form neighbor relationships. This one talks to this one talks to this one. They all start speaking and forming neighbor relationships. They exchange the information that they know, the topology table, their connected networks, and then all of the networks that their neighbors have told them, until eventually the roadmap is solid, as in all of the routers have exactly the same roadmap. Then the routers, one by one, will run the SPF algorithm. Now, I shouldn't say it one by one, like they all wait for the other to finish. Once the roadmap is there, they all figure out the best way around the network. Now, this router up here, we'll say it's router 1. Let's say it gets the topology table formed and it's ready to run the SPF algorithm. What it will do is put itself as the root of the network. It sees itself as the center of everything. Kind of conceited if you ask me, and then it tries to find the best way to all the networks all around. And this is very similar to how you and I act when, let's say, we move into a new neighborhood. You get a new house and you move into the neighborhood, and now you have to plant yourself down and say, okay, my house is now the center of the world, and I need to find the best ways to get to the supermarket, and I need to find the best way to get to the mall and the movie theater. Got to have the movie theater, you know. And you pull out the roadmap, and based on you being the center of the world, you say, from my house it takes 5 minutes to get to the movie theater by just heading out that road. It takes 10 minutes to get to the grocery store by heading out that road. So you figure out the best routes around the neighborhood and around the metropolitan area for you as the center of the world. Same thing for the router. Sits itself as the center of the network and says, okay, what's the best way to get to 10.1.0.0, this network right here? It will look and say, well, I've got one path, which is 1562 plus 10 plus 65 plus 1, and I can get there that way, or I could just go 65 to the 1. It's kind of like, well, I could drive around the entire metropolitan area, or I could just go straight there. So what it does is sees those paths. This path ends up being the one that goes into the routing table. One routing table entry is there. Now this path gets, well, I guess the best way I can say it, thrown away. Meaning the router doesn't remember that path anymore. And this is one of the big differentiators between EIGRP and OSPF. Remember, EIGRP kept the backup paths. OSPF forgets these, meaning they still stay in the topology table. It still keeps the roadmap, but if it ever wants to find this route again, like maybe that one goes down, then it's going to have to rerun the SPF algorithm, again, believe itself as the center of the world, and then find this new path to get there. So it takes a little bit longer when a network failure occurs than it does when you're running the EIGRP protocol. Now, with that being said, all of the routers will run that algorithm and find the best way around the network. But where do these numbers come from? 1562, 65. Well, that is OSPF's metric. Now, here's a big catch. A lot of people will say, well, OSPF finds the best way around the network based on bandwidth. That is a partial truth. In that OSPF does use the bandwidth, but officially its metric is known as the cost. And the cost equals 100 divided by the bandwidth in megabits per second. So if you take, for instance, a 56K connection in megabits per second, 56 kilobits is 0.056, right? Because it's 1/1000th or so of a megabit per second. Divide that into 100 and you end up with 1785. That's what a 56K modem costs. 64K link, maybe one ISDN B channel, 1562. T1 line, 65. And then the list goes on and on, 48, 10, 1, because fast Ethernet is bandwidth of 100 megabits per second into 100, and that ends up equaling a cost of 1. So whenever you're thinking of the OSPF metric, think cost, not bandwidth. It's actually that formula. Now I can read your mind. Through the power of CBT Nuggets video, I can read your mind right now. You know what's going through the back of it? It may be in your subconscious, but somewhere in the back you might be thinking, what about gigabit Ethernet? We've got gigabit Ethernet. We're running it in our network. What about that? What does that cost? And wait a sec. What about 10 gig Ethernet? And I know 100 gig Ethernet is right around the corner. What about all those? What do those cost? Is it a fraction? Well, unfortunately, no. It's not a fraction because there is no such thing as a fraction of a metric. Gigabit Ethernet is a cost of 1. 10 gig Ethernet is a cost of 1. They're all 1 once you go past fast Ethernet because you've exceeded what the divisor is in OSPF. Meaning OSPF came out in the early 80s. I mean, back in the early 80s, if you threw fast Ethernet out there and you said, yeah, someday you'll be running fast Ethernet 100 megasecond, people would go, ha 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 ha, and they would grab their Grey Poupon. That was just a figment of the imagination. Nobody thought that would ever happen. So OSPF was geared like that was the top end, but as we know, it happened, and that is one of the configurations that we will have to tweak in our modern networks of today to adjust this number. When we get to the configuration, I'll show you how to do that. Now let's talk about a concept that has huge ramifications for you when it comes to shared network segments, and primarily speaking about Ethernet here, but it also applies to the non-broadcast multi-access networks. As in, when we get to the advanced configuration of OSPF and we see some wacky network designs, you're going to really want to know what the DR and BDR really do and how they play a role. The way the DR and BDR operate is as a control for a shared network segment. And to understand their role, you really have to understand how OSPF propagates updates to other routers. Like, let's say we have all these routers that form neighbor relationships with each other. They're all plugged into the same switch, same area, same subnet mask, all that stuff. So we have a bunch of neighbors that are plugged in the same Ethernet segment. The way OSPF operates is if this network goes down, the neighbor will immediately send the update to all of its peers, or I should say the OSPF router will immediately send the update to all of its neighbors. Now, when the neighbors receive an update, they will send it to all the routers except the router that originally sent them the update. So this one says, well, I've got an update for you. I've got an update for you. And this one says, I got an update for you, you know, because it received it from this original router. And you can see this madness that happens every single time there's an update. You just get this flurry that happens on the network. Now that does two things. First off, the router, you know, this router's up here, it's like, oh, you know, whenever an update occurs, just because it gets tagged from all the neighbors all at once with this update. So the processor bumps up, and it also affects the convergence time. Because the SPF algorithm has to wait to run after it receives an update, and every single update it receives, the longer it takes that SPF algorithm to run. So here's what the DR and the BDR do. On a shared network segment, one of the routers will be elected as a designated router, and another one of the routers will be elected as the backup designated router. Now, the backup just sits there. It doesn't do anything unless the designated router goes offline. But here's the role that they play. Anytime you are connected to a shared Ethernet segment, let's run through the same scenario again, the network goes down. So wham, this guy loses his connection. Immediately, he will send an update, but instead of sending it to all the routers, he will send it to the DR and to the BDR. OSPF uses multicast for all its communication. So whenever you're talking on a shared Ethernet segment, the initial update will always go to the multicast address. I was calling them a radio frequency, 224.0.0.6, which is a frequency that only the DR and the BDR listen to. Now, the DR will receive the update, figure out what that means for the whole network segment. So it says, okay, what does this mean? This network went down. Let's see if there's a backup path. Let's remove it from the topology table. And then it will send the update out to all its neighbors. So the DR shoots an update to everybody using the multicast address 224.0.0.5. So EIGRP only used one multicast address for communication, 224.0.0.10. OSPF uses two of them. One of them for all OSPF routers, and the other for the DR and the BDR OSPF routers. That eliminates a huge amount of traffic that's going to be sent between all those routers for every single update. Now, I want to make sure you guys catch that the DR and BDR is not a per area thing or a per autonomous system. It's not like of the whole autonomous system, there will be one DR and one BDR. It's not like spanning tree where you have one root bridge. In this case, you have a DR and BDR for every shared segment. So here is another shared segment. On this network, one of the routers will be elected as the DR, and one of them would be elected as the BDR. Now, what does that make the other one? An other. It's neither. It's actually, the official term you'll see in the iOS is DR other is its description. So we have DR and BDR here. Now look right here. We've got a router that's connected to the shared segment. Is there going to be a DR here? You bet there is. This guy. Now, there's only one of them, so he's a lonely DR. He's like a king with no subject to rule. But at the same time, the DR has to be elected for every shared segment. That is not true on point-to-point links, however. On point-to-point links, the only address used for communication is that one, 224.0.0.5, because essentially the Cisco said, well, why elect a DR and a BDR when there's only going to be two routers? It's a point-to-point link, but over here, this one would be elected a DR because it's connected to a shared segment. Does that make sense? So for every single network that's out there where it's a shared segment, there will be a DR and there will be a BDR. Now that does hold true when you come to some of the network designs that frame relay includes. But I'm going to save that discussion when we get into the extremely advanced topics where you really have to control who these are. Now, that's what the BDR and DR do. Let's talk about how they're elected. The election is most influenced by this field in the hello packet known as the router priority. It's one of the fields that we talked about when we discussed in the concepts part 1 that was in the hello header. And inside of there, all the router priorities by default were set to 1. So essentially, every hello packet is an election ballot to become the DR and the BDR. Whoever has the highest router priority wins. But with that being said, they're all tied by default. They're all set to 1, so it has to fall back on a secondary tiebreaker, which is the router ID. Remember the name of the router? Whoever has the higher router ID will end up breaking the tie, and you have to have unique router IDs on all of them, so you're guaranteed that someone will win. Now, I get the question a lot. Does it really matter on, say, an Ethernet segment like this, who becomes the DR and who becomes the BDR? I mean, this one or that one, or should it be that one because they're connected to two networks? You know, which one should it be? Some people say the biggest and beefiest router on the network should be the DR or BDR on an Ethernet segment, which I guess I could back somewhat in the sense that the biggest beefiest router will probably have a little faster processor and be able to send those updates a little faster than anything else, but you won't really notice when you change it around. You could be using a very old router, a very new router. As long as the very old router isn't just on its last leg, processor pegged at 100%, it's going to be all right. It's going to get those updates out in a very fast fashion. Because of that, on a shared Ethernet segment, I have never seen anybody really dictate, at least in the real world, which one of these should be the DR and which one should be the BDR, because just the random chance factor is fine. You know it's going to be elected and you know it's going to happen. Where the election really is important is in the frame relay world, as I was mentioning earlier. And we'll talk about that when we get into frame relay networks specifically. Because if the wrong router gets elected to the DR that doesn't have full connectivity to all the peers, you're going to have a network mess on your hands with OSPF. So the DR, the BDR, those are the ones that are essentially going to be randomly selected by default. Now, the last thing I want to talk about on this topic is how the neighbors look at each other. Meaning, all of these routers will send hello packets out to each other, and they'll all form neighbor relationships of sorts. However, remember when we talked about in the concepts part 1 all the phases that they go through? For example, when this router right here first gets elected as first gets the OSPF process started, it says, okay, I'm in a down state and I'm going to send a hello packet to everybody to see who's out there. And the hello packet goes out, and then it receives hellos back from all the people that received its hello, and it looks at the hello and moves into an init state. Are you remembering this? And it's checking all those criteria, like are our hello timers equal, are our dead timers equal? It's making sure that everybody can be neighbors. And once it makes sure that they're all got the similar configuration, they're all in the same area, they all have the same passwords, etc., this sends a reply hello to everybody, and that moves it into something known as a two-way state. And that was one of the things we talked about. It went from down to init when it first sends it, and then it goes into a two-way state. Now, when you're talking about a shared Ethernet segment, for every single router except the DR and the BDR, that is where it will stay. These routers don't have a need to exchange routing information directly. Remember, that's the whole point of the DR and the BDR, is to alleviate that load so we don't have to send updates all over the place. So these neighbor relationships will stay in a two-way state. And it scares a lot of people. When they do the show IP OSPF neighbors, they see these neighbors that they think are stuck. They're like, oh no, they didn't negotiate a full relationship. They're stuck at two-way. And they think there's a big problem. But there's not. The only ones that will negotiate the full neighbor relationship, remember full is all the way down, going through the X start, the loading, and then they move into a full neighbor relationship, is all the routers that are connected to the DR, and then they will maintain a full relationship with the BDR. And the BDR is just there to allow for a snap fast failover. If the DR fails, everybody already has the relationship established with the BDR, so they're like ready to jump ship, and they're jumping to a router that they know will have the latest and greatest routing information. So don't worry about neighbor relationships that are marked as two-way, because on a shared Ethernet segment, you will only see a maximum of 2 full neighbor relationships. The last concept I want to discuss before we move into the configuration is the flurry of OSPF packet types. Get it? Packets. So anyway, the OSPF process has many different packets that are sent to each other. Now, many of these we've already talked about. We talked about it in the initial concepts video of OSPF. For example, the hello packet, we've already discussed that. It forms the neighbor relationships. The database description packet is the cliff notes of the link state database, so that we can have the routers exchange the whole topology table without giving too much redundant information, because all the routers should have a fairly similar database for the most part, so just the cliff notes are necessary. Now, the link state request we talked about in the last nugget, because we were looking at when the cliff notes are sent to routers, and let me just get a couple routers up here on the screen. When we have router 1 sending its DBD to router 2. Remember, this was a master and slave. The slave will respond with LSRs for any network that it didn't know about. So it would say, oh, I've got a request. Give me all the info for this network or that network. And that was the link state request. Now, I said the response came back as, anyone remember what it is? Come on, you remember. It was an LSU, a link state update that was passed back to the slave routers that would update their database with all the information about that route. So with that being said, we've talked about a lot of these, but you see a few more packet types in here that we haven't touched on yet. And I want to officially throw these out to you because you'll see them all over the place when you read OSPF documentation. The biggest one is this: a link state advertisement, an LSA. Link state advertisements are updates about individual routes. Now, let me back up a little bit in saying that when I said an LSR was sent over to the master and an LSU was sent back, that was somewhat of a partial truth. Now, I'm not telling you a lie here. I'm just telling you a partial truth. And that if you were to grab a packet sniffer and see the packet come across, it would come across as an LSU. But an LSU, defined specifically, is like a big ol' envelope. Inside of that link state update will be one or more LSAs, which is an update about an individual route. So here's the concept. Rather than having a slave send a link state request and say, well, I need this network and that network and that network and that network, and the master going, okay, here's an LSU, here's an LSU, here's an LSU, here, giving him all these LSUs for all these updates, it said, well, why not be more efficient? Why not send a link state request? Maybe we can get by with one packet that's asking for updates of 50 different networks. And instead of sending 50 different LSUs back, let's just send one big LSU envelope, which if you open it up inside of there is 50 different LSAs, individual updates about the networks. Think of it as like if I went out to the mailbox today and I pulled out this envelope and it was those coupon mailers. You know, the coupon, is that how you say it? Coupon? Coupon? A coupon mailer where you get coupons for all the local retailers around here. Now, all the retailers are all different coupons and all different establishments, but they all banded together and got their coupons distributed through one company. In the same way, you have the router sending a link state update with LSAs about many different networks, 50 of them to be exact, which makes it much more efficient when you're sending those across. So the partial truth I told you was that it responded with an LSU, but what I didn't tell you was inside of that LSU was a bunch, well, one or more, I'll say, LSAs that have all of the updates that were requested by the slave. The last one that you see on this screen is the LSAC, which is the reliability mechanism for OSPF. OSPF is its own transport layer protocol. Remember the OSI protocol stack? You had, physical layer, data link layer, network layer, and the transport layer. And right here at the transport layer, you had things like TCP and UDP and so on. Well, OSPF doesn't use TCP, and it doesn't use UDP. It is its own layer 4 protocol. So instead of relying on acknowledgments from the TCP protocol to get its way around, it has its own acknowledgement. And every single update, every single request, every single message that's sent between routers, except for the hello message and, of course, the LSAC, you're not going to acknowledge an acknowledgement, is going to be acknowledged, making OSPF a reliable protocol that you can guarantee every update gets there when it's sent. Well, there's the ticket, the last piece of the OSPF concepts before we move into the configuration. That was just the concepts to get you into the basic configuration of OSPF. Just wait, there's more. There are many different concepts that we'll talk about as we splice in the configuration and get into the advanced stuff. So to hit the high points, we did talk about the OSPF cost, which is its metric, 100 divided by the bandwidth in megabits per second. We then moved into the DR and the BDR, the designated router and the backup designated router, which are used on shared Ethernet segments and NBMA, non-broadcast multi-access networks, the clouds, to manage the amount of updates that needs to be sent between neighbors. Finally, we officially discussed every single packet type that you'll find in OSPF. And what you'll find as we get into the more advanced stuff is that there are sub-packet types. For example, we talked about an LSA, but there's actually 11 different LSA types that are defined out there. So, a lot more to talk about as we get into this. I hope this has been informative for you, and I'd like to thank you for viewing.